Okay, 11.2 is radioactivity. Okay. In this chapter, you guys need to understand few things lah. Number one, you need to be able to explain about decays. There are 4 types of decays: alpha, beta plus, beta minus, and gamma decays. And then you need to be able to do some calculation that involve these 4 formulas. Actually, it has another 1 formula. It's not given inside here. Okay, anyway, radioactivity decay is defined as the phenomena in which an unstable nucleus disintegrates to acquire more stable nucleus. So, dia always daripada unstable towards more stable nucleus without absorb and external energy. Okay, this integration commonly involves the emission of an alpha particle, beta particle, and gamma ray. Okay, these 3 separates into 3 separate decay lah. The radioactive decay is a spontaneous reaction, unplanned, cannot be predicted, and independent of physical condition and chemical changes. Okay, this reaction is random reaction because the probability of the nuclei decaying at a given instant is the same for all the nuclei in the sample. So if you have a sample that consists of lots of nuclei, nuclei ni macam satu ketul lah, macam satu atoms tu. So kalau ada banyak kan, probability of nuclei decaying are the same. Okay, there's 4 types of decay. Like I told before, we have alpha, beta, and gamma. So if we separate into that, have 3 lah. Tapi beta tu ada 2 kan. So alpha, beta, and gamma. Okay. So beta ni we can separate into 2 more. One is beta plus, another one is beta minus. Okay, maybe saya tak beta minus dulu kot, sebab tadi saya explain beta minus dulu. And then alpha ni normally dia release alpha particle, kita boleh letak simbol dia sebagai helium or alpha itself. Okay, yang penting nombor dia tu 42. Okay, you really have to memorize lah yang apa tu, simbol dia dengan dia punya nombor tu. Kalau beta, you can write as B minus 2 ataupun you write as electron charge, elementary charge. Screen saya lagi ni, okay, lagi sikit. And then kalau beta plus, you can write as 0 and 1 instead. And gamma, you can represent with a symbol gamma. Okay, so far, any question you want to ask?
Okay, sir.
Okay, tak ada. Ini just a simple things, okay. And then if you want to look into detail, most likely,
No, sir.
When they ask you question regarding the decay, the first thing that they might ask is that they might ask you to write down the equations. Okay, so equation ni macam dekat chemistry jugalah. The key thing here is you basically want to have a balance left and right to your nombor. Okay, so here an example, maybe dalam exam dia kata alpha particle being released inside the reactions ataupun decay. Okay, write down the equations. Okay, so you can write in terms of helium like that, or you can also write in terms of alpha itself. Dua-dua diterima. Okay. And then most likely yang PB ni, yang decide kan, kadang-kadang dia tak kasih pun yang daughter dia ni. Okay. So if they didn't give you the PB, you can use that one as Y ataupun X. It's up to you lah. Basically just an unknown. Kamu boleh gantikan lah kalau tak diberi. If it is given, you can use straight away. So this one will be helium tambah Q. Okay. So after you put helium, you have to balance left and right. Okay, so right hand side ni kan, you have 4 and 2. So basically PB ni kamu kena tallykan lah. This one becomes 214. And that one becomes 80. Okay, you can always check again. 214 plus 4 is equals to 218. 82 plus 2 is equals to 84. Okay. And then yang heat ni, yang tenaga ni, just put it over there. Okay. Normally this one in terms of heat. Okay. Ada yang tak clear tak about this one? Yes.
Yang helium tu memang kena tambah ke?
Memang kena tambah betul. So kita memang kena letak. So sebab ini adalah hasil daripada reaction ni. Okay. Dia decay. Daripada decay tu dia produce helium. Alpha particle lah. So alpha particle tu memang duduk di belah kanan dan memang dia adalah tambah. Dia maksud kamu kan tambah kan. And then if this one is 4-2, nak balance kan kamu kena tengok je lah kiri dan kanan tu. Menjawab tak soalan kamu? Rasanya okey kot tu kan. Okay.
Faham, sir.
Benar lah. Okay, alright, good. Okay, the next decay is beta, that produce the beta particle. Beta particle ni ada beta plus dengan beta minus. So beta minus kita panggil sebagai elektron lah, saya tulis balik atas sumber. So beta minus, okay, ataupun biasa kita panggil dia sebagai elektron. Okay, when we try to represent with a symbol, normally we use a symbol of E. That means elementary charge tu lah, E tu. And then -1 tu sebab dia adalah elektron. Kalau dia adalah positron, you put it as +1. Okay. And then dia ada formula dia lah. Formula ni tak ada apa pun. Just a simple thing. Just says that as since this one is -1, we have to add that one with another one lah. Tambah 1. Dan Z tu kamu tambah 1. Okay, let's try to look at the example I'll give you here. Okay, in this example, you can see that here TH, the decay to PA. Again, I repeat, kalau PA tu kalau tak sure nak tulis apa, you can simply put X ataupun Y. Sebab dia adalah beta minus punya decay, so dia akan produce electron. Okay, you can put B atau beta, or you can put E like this lah. Now once you put this one, you have to check whether it's balanced or not. So you have 2, 3, 4 on the left hand side. This one is 0. So atas ni berapa? Atas PA tu
234.
yes, 2, 3, 4 juga. It doesn't change.
2, 3,
So
4.
2, 3, 4 on the right hand side here. And then yang bawah tu dia jadi berapa?
91.
91. Okay, very good. Okay, and then you can always check lah. 2, 3, 4 plus 0 is equals to 2, 3, 4. Right hand side is equals to left hand side. Correct. Okay, yang this one 91 minus 1 is 90. Correct as well. So most of it is correct lah. And then don't forget, okay, to include Q. Okay, dan this one memang kena ada. Okay, and ada certain years dia memang particular. Kalau tak ada tu dikira salah. So might as well you put. Okay, the next decay is beta plus, also known as releasing a positron. Beta plus positron. Okay, you can represent with symbol of elementary charge. Okay, tapi this time instead of -1 dekat bawah tu kita letak dia sebagai +1. Okay, that was beta with symbol. Pun boleh tak guna. Okay, so formula a little bit different. Okay, kalau tadi Z plus 1, now it is Z minus 1. Kita balik je lah. And then kalau tadi positive, sorry, tadi negative, now it's positive. And then if you notice over here, dia ada extra D. Only for beta plus untuk positron that you have to include dia punya V. Yang lain tak perlu. Yang ni dia kena ada extra. Okay, V ni is a neutrino, is a byproduct lah daripada decay process tu, dihasilkan produk lain juga, which is the neutrino itself. Okay, contoh over here I have P over here, P11. Okay, and then dijadikan, dia hasil dia, daughter dia adalah N. Ini adalah beta plus punya decay, so plus E01. Okay, so N tu dekat atas dia apa?
1.
1.
One.
Very good. Yang bawah tu?
0.
0. Okay, very good. And then don't forget to
Kosong.
put plus V and then plus Q. Okay, so dia memang simple je. So you just have to read the question properly and then just follow the punya reaction. Okay, then the last one is about gamma ray. Okay, gamma ray ni is slightly different because it's not actually a particle, but this one adalah high energy photon. Okay, so high energy photon means that they release energy lah. Kalau tadi dia release energy in Q, kan? Yang ni dia release energy in terms of photon. So here initially you have Ti. Okay, so after they release the photon, dia masih lagi Ti, dia tak berubah. Just that energy dia berkurang. Kalau yang ni daripada excited state, now dia dah tak ada lah, daripada excited state, dan plus gamma. Itu je. Okay? You don't have to put Q lah sebab all the energies now becomes the photon. And normally gamma punya decays ni kadang-kadang dia include dengan benda lain juga. Contohnya kan dia suka gabungkan macam helium dengan gamma. Sorry. Dia akan cakap reaction tu, decay tu, dia produce alpha particle dengan gamma. So if the question state like that, kita ringan. Okay. Okay. I don't know why I can't touch my screen now. Okay, dia hang. Mana tadi ya? Okay, katakan ada combination of helium dengan alpha particle. Contohnya dia kata TO ni bila decay, dia release alpha particle dengan gamma ray. So instead of Q, kamu tukar daripada gamma, yang lain sama je. You guys understand or not? Any question you want to ask? Okay.
Yes, sir.
Okay, let's try to look at the next part. Okay, yang tu yang first part lah. The first part tu biasa soalan yang awal lah. Maka dia biasa dalam 2 kot kalau ditanya. Okay, so ada sedikit lagi theory before we go to calculation. Okay, this one show the comparison between the radioactive radiation. Okay, so in terms of deflection, okay, kalau deflection, okay, you can see that the gamma does not undergo any deflection lah due to electric field atau magnetic field. Okay, mainly because dia tak di-charge. Okay, so kamu tahu kan kalau electric field punya deflection tu dia kena ada charge. So kalau yang alpha dengan beta dari charge, so dulu ni akan deflected lah. Kalau yang gamma tak ada. Lepas tu in terms of ionization power, yang paling strongest adalah alpha. Tapi yang alpha ni paling penetration power dia tu paling kurang. Dia susah nak tembus benda lah. So basically kalau kamu ada dinding, biasanya dia dah terhalang daripada alpha particle. Okay. So yang lain apa, itu cukup yang penting. Yang charge ni kamu tahu lah, ini adalah positif 2. Kalau yang beta tu adalah elementary charge. Okay, this one adalah example. Kalau macam tadi gamma tu, kalau dia lalu dekat electric field, dia tak deflected lah, dia just go straight. Kalau yang lain tu dia akan deflected. Okay. Now about calculation. Okay, the first thing that you guys need to know is about decay constant. I rewrite this one. Decay constant. The symbol that we use is lambda. Okay, but this time lambda ni bukan wavelength lah, dia adalah decay constant untuk chapter ni unit dia kadang-kadang per second ataupun per unit time lah. Okay, law of radioactive decay state that for a radioactive source, the decay rate is directly proportional to the numbers of radioactive nuclei. Okay, radioactive nuclei ni nuclei yang radioactive lah, remaining in the source. Okay, dia kata rate of decay rate ni directly proportional dengan numbers of nuclei left in the source. So n. And then this one kalau kamu perasan dia ada negative. Negative ni indicates that rate tu berkurang. I mean dia punya nilai dia tu berkurang. That's why dia adalah negative. Okay. And then if you want to change directly proportional and you want to change to equal sign, we have to put a constant. And so constant here basically is the decay constant, lambda tu. So this is one of the equation, one of the first equation that you guys need to understand. dN dt is the rate of decay. Negative here indicates that the rate to menurun. Okay. And then this one is a decay constant, and N2 adalah numbers of nuclei. N2 unit dia adalah nuclei. N2 sebenarnya biasa sama banyak dengan atoms lah. Kalau kamu ada 10 atom, maksudnya kamu ada 10 nuclei. Okay, so dia ada derivation dia. From here, I can bring yang dt to the other side kan. And then saya will integrate and so on. And I will end up with this equation. Okay, this is another important equation. N equals to N naught E negative lambda T. Okay, this one is the exponential. Okay, I think you guys put calculator is quite canggih kot. Sebab tak ada masalah. You guys can simply press the calculator to get the answer. Kalau calculator saya dulu yang lama tu saya leceh sikit nak selesai ni, saya kena take ln and everything. Okay, but make sure you know how to use the ln in case you have to use. Okay, just bring this one to the side. Okay, and here represent numbers of remaining nuclei at certain time t. Okay, so this one equation ni dia memberikan nilai n bila kamu ada specific time. Contohnya nak cari, katakanlah initially kamu ada 100 nuclei yang radioaktif lah. Itu dia punya N naught. Okay, this is N naught. After 2 minit, so this one, dia 2 minit lah. And you have to change to second, times 60. After 2 minutes, berapakah bilangan N yang tinggal? So, you just have to substitute inside the formula and you get this value, N nuclei. Okay, if you want to plot this one in terms of graph, dia akan jadi macam ni lah. Contoh tadi, ini adalah 100. Okay. Benda yang penting saya nak tunjuk kat sini sebenarnya adalah ini. N naught over 2. So, separuh daripada initial dia tu is what we call half-life. Okay, the time taken untuk dia sampai situ is basically half-life. Inilah. Ini half. Yes, here it says from the graph, the life of any radioactive nuclei is infinity. Therefore, to talk about the life of radioactive nuclei, we refer to its half-life. Sebab dia infinity, kita nak cerita pasal dia, kita cerita pasal half-life. So, half-life tu ada nilai. Okay lah. And half-life ni depends dengan material. Contoh kalau macam PO tadi, dengan PB, dia punya decay half-life dia lain-lain. Okay. Okay, the symbol that we use for half-life is T half. Memang obvious lah, T half tu is half-life. Equation dia adalah T half equals to ln 2 over lambda. Okay. Dia ada derivation juga, that's why dia ada ln 2 tu. Okay, tapi again, just show you the important bits. Okay, so T half tu unit dia dalam masa lah, contohnya second ke, minute ke, year ke, ataupun months. Biasanya kalau nak SI unit second. Okay, kalau ini dalam second, that means lambda ni jadi per second. Okay. Biasanya maybe they will ask you to calculate lambda instead. So most of the time equation ni kamu pakai macam ni. Instead of the other way around kan, kamu pakai yang lambda ni yang kamu nak cari biasanya lah. So lambda tu dia akan ikut T half tu punya unit. Kalau T half tu year, dia jadi lambda tu jadi per year. Macam ada soalan tak so far?
Tak ada, sir.
Okay. So the next part is about decay rate of radioactivity sample, radioactive sample. Okay, decay rate of radioactive sample ni sebenarnya kan kita boleh cakap dia sebagai activity. Okay. So activity ni actually represent dN over dt, sama je, cuma dia adalah simbol yang berbeza, tapi benda tu kira benda sama. A is equals to dN over dt. dt tu datang di atas tadi, kat sini lah. Okay. Okay, so and this one, A ni dia ada unit dia yang spesifik. Okay, A dia sebenarnya adalah 1 decay per second. Sorry, decay per second lah unit untuk A. Tapi kita rekaskan decay per second tu sebagai becquerel. Okay, 1 decay per second is equals to 1 becquerel. So if you calculate everything in SI unit, final answer for A is in BQ becquerel lah. Okay. Alternatively, dia ada lagi satu unit which is Curie. Curie ni kalau dia suruh kamu convert, they will give you this value. 3.7/10^10 ni they will give you inside the question itself. Ataupun dia kasih dalam list of constant. Biasanya dia letak straight dekat dalam soalan. Okay, and then that one just the unit for A. So kalau tadi, yang asalnya tadi daripada law of radioactivity kan, law of decay tu, yang dn dt is equals to negative lambda n. So sebabkan dn over dt is your A, I can write that one as this one. Okay, equation 2 now become A is equals to negative lambda n. Okay. This equation tak diberi dalam formula sheet. Previously dia tak berilah, dan this time saya tak tahu. So kita expect dia tak beri jugalah. So you guys really need to understand that A is basically equals to dn over dt. Sama je. So dia masukkan ni sebagai A, dia jadilah equation yang baru ni. Okay, so kalau tadi kita ada initially kan kita ada equation of n sama dengan n naught eksponen negatif lambda t tu. Kalau saya replace n dengan n naught ni sebagai negatif lambda n tu, potong-potong lah jadi A dengan A naught. Okay. Dan ni pula cerita pasal activity at specific time. A dia tu bila time tu berapa. A naught ni masih sama lah, initial activity. And remember A ni, unit ni adalah becquerel. Okay, summary. I just do a quick summary. What you guys learn today, number 1, you guys learn about decay. There are 4 types of decay. Decay number 1 is alpha. For alpha, normally you guys represent a symbol of helium. Okay, ataupun alpha sendiri. And then you have another decay which is called beta. Okay. So kalau yang alpha tadi dia punya produk dia tu alpha particle, daughter dia dengan Q. Ini yang daughter saya tak tulis lah, memang tahulah. Tapi saya nak tunjuk yang Q tu. Okay. Kalau beta pula dia terbagi kepada 2. You have beta plus which is ada, beta minus ada. Okay. Kalau untuk beta plus, kamu ada byproduct ini tambah V tambah Q. Jadi extra. Kalau yang negatif tu tambah Q saja. So remember that one. That one is neutrino. And the last decay is gamma. Okay. Kalau gamma ni paling senang lah, ditambah gamma saja. Okay, that one is about decay. Ada 4 and kamu kena tahulah setiap satu tu apa. Okay, the next part you learn about dn over dt. Ini adalah rate of decay. Negative lambda and lambda tu adalah decay constant. Okay. And then as a result, okay, kalau saya derive ini, saya boleh tulis dia sebagai n sama dengan n naught eksponen negatif lambda t. Okay. Yang lambda ni, remember lambda ni adalah ln 2 over half-life. Sebab apa? Sebab t half sama dengan ln 2 over lambda. So kalau saya rearrange lambda ni kan, saya buat naik, jadi ln 2 over t half tu yang masuk dalam ni. Okay. And then you guys also know that yang dn dt ni akan represent with A. So A ni sama dengan negatif lambda n. Okay. So the only equation that relates A dengan n is this one. A sama dengan negatif lambda n. And then at the same time, you can write this one as A naught equals to negative lambda n naught. Kita tengoklah kalau A tu dekat 5 saat, N tu dekat 5 saat. Kalau A tu dekat 10 saat, N tu dekat 10 saat. If you are talking about initial A, N dia pun adalah initial. Okay. That's why you can write down this equation. Jadi A equals to A naught eksponen negative lambda T. Okay, any question? about this?
No, sir.
Okay, there's no question. Kita try tengok dia punya soalan. Okay, if I'm not mistaken, this one adalah question number 8B. Okay. Semalam kita buat sampai 8A kan? This one is 8B. Dia kata nuclei of manganese undergoes a decay to form nuclei of chromium. Proton numbers of 24. Write the equation for this decay process. Identify the type of decay. So dia nak saya tentukan lah, itu adakah ia adalah alpha decay, gamma ataupun beta plus or beta minus. Okay, so first of all you have to write down the punya equations lah, sebab dia memang suruh tulis equation dia dulu. Okay, so cara dia senang je. I'm going to show you how to write down. Tulis the parents dia, manganese tu, and then this is the decay process. They produce chromium. Okay, dia kata proton number tu 24. 24 tu nak duduk kat mana? Atas ke bawah? Proton number.
Bawah.
Bawah.
Very good. So bawah ni 24, yang atas tu kita isi sama lah. Kita cakap bahasa atas sama je. So if it is like this, then you can add. Okay, sebab dia ada beza kan. So yang belah kanan ni 24 only, dekat on your left is 25. So belah kanan ni kamu boleh tambah 1, atas tu 0. Okay, so straight away kamu boleh tulis E lah dekat sini, or you can write beta. Okay, and then kalau ini adalah positron, dia akan release apa, ingat tak tadi?
Saya nak satu.
Q dengan apa lagi satu? V.
V.
Yes, neutrino dia. Okay, very good. Okay, so now lagi dia nak cari type of decay. So type of decay ini adalah beta plus decay. Okay, this one's for question 1. Question number 2. Identify the antiparticles corresponding to the particles emitted in the decay process. Okay, so dekat sini particle emitted ada 2. Okay, so dia ada E tu dengan V tu kan. So particle terbanyak nampak. Okay, situ dulu. Dengan antiparticle. The particle emitted in this case dari 2. Yang pertama tu adalah positron. Ini adalah positron. Yang kedua adalah V, which is neutrino. Okay. Antiparticle to these two are positron. Anti dia apa? Kamu rasa? Positron anti dia apa? Electron. Okay. Apa ni? Nasional tekan tu apa? Tu yang memang nak tanya soalan. Kalau elektron, ada nak tanya ke? Tak ada. Okay. Lepas tu kalau neutrino, dia punya anti dia adalah anti-neutrino. So simbol dia adalah V, lepas tu ada bar. Okay, any question for the first question?
Tak ada, sir.
Yeah. Okay. And then the next question is question number 9A. They ask you to calculate the half-life of Bi. Dia kasih half-life of Bi is 5 days. So, can straight away write lah. The half dia adalah 5 days. Calculate the decay constant. So, you basically want to apply the half equation sama dengan ln 2 over lambda. Dia nak cari decay constant, so dia nak cari lambda. So, lambda here is equals to ln 2 over 5 days. Okay, kalau kamu leave it like this, in terms of days, Untuk lambda tu akan, unit dia akan days per days lah. Okay, tapi kita nak tukar lah. I think screen saya lagging kot. So daripada hari nak tukar ke saat berapa, darab berapa ni? Hari ke jam berapa?
24.
24, yes, correct. And then you have to multiply it from hours to second. Darab 60, dapat 60 minit. Darab 60 lagi, dapat second. So darab 3600 straight away lah. So lambda here is equals to, kira berapa dapat ni? .6
Betul sir.
Okay, times 10 negative 6 per second. Okay, sebab apa second? Sebab kamu dah tukar tadi tu dalam second. Okay, that was for A1. For A2, they want to calculate the activity of 10 gram. Okay, and this one you have to apply your knowledge from the chemistry. Kalau dikasih mass, you want to change to numbers of atom, macam mana? Bukan ada sini kan? Ada tak? Sini. Kalau kamu dari sini, nak ke sini, kamu bagi dengan apa?
Molar mass.
Yes, bagi molar mass. Kalau daripada mol nak ke atom, kamu darab bergaduh number. Okay, very good. Yes. Okay, in this case, molar mass tu dia tak kasih specifically lah. Kalau chemistry biasa dia kasih kot M besar tu berapa. Okay, yang here kita ambil yang average lah, which is 210. So, M dia sebenarnya adalah 210 gram per mole. So, fizik biasanya memang macam tu. Okay, kita ambil je nombor kat atas tu. So, now you can calculate the numbers of nuclei. So, soalnya nak activity. So, first you have to calculate N. And once you got the N, you can substitute back inside this equation. A sama dengan negatif lambda N. Kita nak cari N tu dulu lah. Okay. So, to calculate N, kamu kira mol dulu. N kecil. Mass divided by molar mass. So, 10 divided by 210. Like 0.0476 mole. Okay. Once I got the mole, I can change to atoms ataupun numbers of nuclei. I hope I got the numbers correct. Good. So 0.0476 times 6.02 exponential of 23. I got here 2.87. 865. Okay, 87 now. Times 10 to the power of 22. Okay, nuclei. Unit dia kan tulis nuclei. Once I got the N, I can calculate the A. A is equals to negative lambda N. Tapi negatif tu kamu boleh ignore lah. Sebab kamu nak kira dia A kan. Negatif tu masukkan dia decay. So, lambda tadi dah kira. Lambda dia adalah 1.6 dah 10 negatif 6. Nuclei numbers dia adalah 2.87 times 10 to the power of 22. Saya dapat sini 4.59 sama tak? Posisi sini. Okay, dapat ke tidak? Unit dia apa?
BQ ke sir?
BQ, yes. The unit will be BQ, becquerel. Okay. Okay. So, basically, we answer question A Okay, the next question, kita buat lagi satu lah. Now we try to do one more. Okay, dia kata the activity of sample elicited change from 1000 becquerel to 800 becquerel in 20 minutes. Okay. Subtract the decay constant, half-life, initial numbers of radioactive nuclei, and so on. Okay, yang B tu dia kata 1000 becquerel dengan 800 becquerel in 20 minutes. Maksudnya initially A0 dia, okay, kalau macam ni kan saya suka buat macam timeline tau. So when T is equals to 0, we are talking about initial quantity. So A0 dia sama dengan 1000 becquerel. Okay. Itulah. Lepas tu bila dia dekat T after 20 minutes, dia punya A dia now becomes 800. Okay. The first question they want to calculate the decay constant. To calculate decay constant, you can straight away apply formula that has A naught tu. Kamu pakai A equals to A naught exponent negative lambda T. Okay. Where your A is 800. A naught is 1000. Lambda dia adalah, kita nak cari, time dia adalah 20. So 20 multiply with 60. Kamu dapat second. So if you have your calculator, I think you can straight away kira kot lambda ni berapa. Kalau saya, I might have to take ln. Maybe saya tunjuk cara kalau saya kena buat lah. So I have to bring 800 to 1000 to the other side. Yeah, so dia jadi 800 divided by 1000. I got here 0.8. Okay, and then I have to take ln on both sides. So yang ni dia jadi ln E. Yang atas tu dia turun bawah. Okay. And then ln 0.8 is equals to 0.223 negative divided by negative 120. Ln E2 is equals to 1. So my lambda now becomes 1.85, 1.86. Understand? Negative 3. Unit dia apa?
Meter.
Per second. Okay. By the way, kamu dapat jawapan sama dengan saya ke tidak? Kamu try tekan sendiri kan? Ni bukan 120 kan, 1200. Sebab
So saya dapat 10 negative 4.
sebab 1200. Okay. This is 1200. Okay, so if you press again, you should get negative 40. Very good. Okay, that one's for 1. Okay, the next question, they want to find the half-life. So, kamu dari lambda senang lah. So, T half is equals to ln 2 divided by lambda. So, your T half now equals to 3726. Sama tak? 60 second. Okay, so kita dah pakai SI ni, so everything, our answer semua dalam second. Okay. And then the third question, dia kata initial numbers of radioactive nuclei. Initial numbers of radioactive nuclei. Okay. So, now, macam saya cakap lah, the only relation between A dengan N is this equation. A is equals to lambda N. Dia ada negatif kan, tapi negatif kita ignore. Okay. So kalau kita nak cari knot initial, kita letak knot dekat dua-dua side lah. Jadi A knot dengan M knot. So A knot tadi kita adalah 1000 becquerel. Lambda tadi kita baru kita kira 1.86 times 10 negative 4. So N knot here is equals to 1000 divided by 1.86 negative 4. So that is 5.38 times 10 to the power of 6 nuclei. Okay. So then I can calculate. Itu je lah. Soalan ni nak tu je. Yang last tu boleh kata numbers of radioactive nuclei decay within 20 minutes. So basically if I copy this one, okay, the last question ni dia kata after 20 minutes dia nak cari berapa banyak yang dah decay. So you already have the N knot, kita baru je kira N knot. So now you have to calculate N, okay, so that you can calculate berapa banyak dah decay. So how many decays, basically N knot dia tolak dengan yang akhir dia. So akhir tu lagi kecil kan, so saya letak N knot minus N. Okay, to find N, you can use this formula lah. N sama dengan N knot exponent negative lambda T. Lambda tadi dah ada kan, lambda sama dengan this one. Let's copy this value. Okay. So exponent negative 1.86 times 10 negative 4 multiply with time, which is 20 tadi darab dengan 60,002 tu. To be careful with the negative, negative tu jangan lupa letak dekat exponent tu. So here I got 4.3. Nuclei. Okay. So basically that value duduk dia dekat sini. Okay, so now I can find the difference berapa banyak yang dah berkurang by minusnya lah 5.38 minus dengan 4.3 times 10 to the power of 6. So you get 1.08. So 1.08 ni amount of nuclei yang dah berkurang.